Hi, I'm Chairul Bahri. I'm a postdoc with David Rowe between 95 to 2000, 2001, just right before or about 9/11. This is a turning point in my life, actually. David and Yuna are very generous to accommodate us both, whatever colleagues that and students. I've been in contact with Hubert Hong Chen just briefly before she graduated, or probably after her graduation. And definitely Steve Bartlett. I'm looking forward to meeting him anytime. And Peter Turner was the one who and tried it also more. And in fact, when I came back to LSU, Peter also came down to Baton Rouge, and we have some contact with that. I had a privilege to speak with David in the last month, probably about a week before he celebrated his life. It's quite moving. He's always cheerful, and I'm glad, and I share this sentiment with Yuna and Amanda to pass my condolence. And he is a really great mentor for me, and and indeed he, as Jerry has said, he always challenged tooth and nail on your thought and your ideas, and this is I cherish tremendously. Let me see whether I can share my screen now. So I may share my screen. That will be the easiest way for me to do it. Is it picking up?
We're looking at a spinning wheel, or at least I am, Chairul. It seems like it's trying.
Yeah.
There we go.
Okay, we see it now.
Okay, let's see how I can slideshow. I do it here. Okay. I currently a limited term associate professor at Kennesaw State University. Kennesaw State University is in the suburb of Atlanta, greater Atlanta area. And I'm still affiliated with Georgia Tech. This is the way I keep my physics interest. Prior to Georgia Tech, I've been with University of Notre Dame. Despite the fact that I've been in the banking after I in 2004 when I joined with Hibernia National Bank that has been acquired by Capital One, and then moved to State Farm where I get in contact with Mark Caprio, and he invited me to join University of Notre Dame. And later on, when I moved to Atlanta upon my employment with BBVA, this is a Spanish bank, until 2019. And I basically resigned from the bank, and immediately we have a pandemic, as well as that bank itself has been acquired by PNC Bank. So that's my short story between physics. The slide I share right now is really my patient, and as well as my my collaboration with David during my stay at University of Toronto quite some time. And then come to the conviction that we are facing something substantial here in physics of many body system. There are a couple of topics or items that I consider David has his legacy on. One, along with the late George Rosenstiel, this in the symplectic model back in 1977. I think it has stood up and become the hallmark for nuclear mighty-body system. And I was so fortunate to be able to live in the two sides of the world, in Baton Rouge, under the guidance of Jerry Dreyer, who is in one side of this model, algebraic fermionic model, and also with David, which I joined when I joined the team at the University of Toronto in 1995. Immediately after my graduation in late 1994. Which looks like from the bosonic approach of the model. And later on, David gave a task to me to see whether we can find the symmetry in the two-body interaction, the pairing model within the framework, a symplectic framework. And this approach, which he believed to be the success of phenomenological model in nuclear physics, in nuclear spectroscopy, where one find so many rotational band, and he introduced the concept of embedded representation of a symmetry. Where Bear is a graduate student at that time, probed in much deeper level, and Hong Chen, who just graduated upon my arrival, from looking at the perspective from the pairing interaction. So we are able to demonstrate that there is a quasi-dynamical symmetry, where the symmetry or the band that one observes is simply the manifestation of the new, or could be the old, depending upon how you look at it, because it just comes into different names. But we toss the term quasi-dynamical symmetry here. So the way that we normally do in nuclear structure physics, we have a Hamiltonian, or the time-independent Schrödinger equation, where the Hamiltonian is an operator act on the Hilbert space characterized by the wave function. And we specify that the generator is labeled by X as the generator of an algebra if one is taking the phenomenological model. If I take an SU3, which becomes the precursor for symplectic, one can easily express the interactions in the term of SU3 tensors. SU3 tensors, meaning that any interaction, realistic interaction, one body, two body, in fact, you can go further, three body, four body interactions, if you like, can be expressed in the term of irreducible tensors of SU3. Looking at the two-body interaction, one can characterize a scalar interaction, a vector interaction, and tensor interactions. Scalar interactions mean that the spin characteristics of that operator is a spin zero, scalar. Consequently, it has the angular momentum zero object, while vector interaction has the spin one characteristics, which lead into the vector, and finally the tensor interaction. So this is the most the possible interaction that we could come up with. In the term of SU3 irreducible tensor, one can identify that scalar interaction will be taking the even lambda mu, which are the irreducible tensors of SU3, while the vector interaction may take a odd lambda mu operator values, and finally the tensor can have an even or odd to lead into the angular momentum 2 or tensor operator. Definitely things are getting more complicated when you go to the three-body interaction and the four-body interactions. However, we strongly believe even for at the nucleonic degrees of freedom, the three-body interactions plays a very important role to the fact that to bring the binding energy to the right experimental value. The previous study in the scattering phenomena, and when you derive a three and four body interaction, normally discard the four body interaction. However, I still strongly believe that this four body interaction need to be included due to the fact that the alpha particles cluster very strongly throughout the nuclear system. Now we get into the symplectic symmetry. The symmetry itself, the symmetry of Hamiltonian equation. One can nail down the operators, axis, the coordinates, and the momenta p's as a fundamental irreducible tensor of symplectic symmetry with the Dynkin label 1, 0, 0. Just to remind you, this operator is finite. You have a six-dimensional object here in the term of a irreducible representation. It is tensor of sp3r, but it covers the non-unitary characteristics. But as far as the tensors, we are really good at that. And the generators of sp3r can be characterized by the quadruple moment, and then the shared tensor, angular momenta, and the kinetic momenta term, which belongs to a joint irreducible tensor to 0, 0. Again, this is a finite dimensional. We have it has 21 dimensional space for this object. But the space itself is infinite dimensional because the characters of the SP3R. Jerry has shared a significant in his slides, which I'd like to reintroduce here. The framework that we deal with the harmonic oscillator shells, which turns out to be the dynamical symmetry of a symplectic irreducible representation. But this is infinite dimensional, but the space itself is a unitary. For one particle, it has a one irrep, one unitary irrep, 0, 0, 0, and 1, 0, 0, but it is unbounded from the above. 0, 0, 0 belongs to the even oscillator shell, while 1, 0, 0 belongs to the odd oscillator shell. Then when we characterize the atomic nuclei, so we basically fill up the particles according to the oscillator shells, and voila, we are able to specify the lowest height of the SP3R irreducible representation that coincide with the shell model SU3 irreps. Let's see. So I'm taking this one from Christina's picture. So in this approach, in the no-core shell model approach, as Jerry pointed out, launched by Navratil, Bahri, and Barrett, this is a particle-driven. So individual particle which carries a single shell quantum number, which we forget that this n quantum number is really the oscillator shell quantum numbers to be the basis for this computation. Okay. Sorry, here, let me see whether I can. While on the LSU group, instead of taking particles, the models are driven by the shapes. And this shape is characterized by SP3R irreps. So instead of taking a particle or particles of quantum number, so you look at the SP3R irreps, a linear combination of them to generate the many-body eigenstates of the Hamiltonian. So let's go back and see how one can come from the particle-driven representation into we aim for the symplectic couple scheme. So in single particle structure, so the basis states will be characterized by the oscillator shell number n, and this is has a angular momentum, single angular orbital angular momentum L, coupled to total angular momentum J with a spin half for each nucleon. And then basically you label, you characterize individual particle in this way. And then based on the nuclear closed shellness, you're only interested in the valence particles to specify the basis. But in the no-core shell model, one characterize all the possibility, in fact, allow the particle excitation to the next oscillator shell. Computationally, this is definitely more appealing because it doesn't require much coupling scheme. So this, in the beginning, it supersedes the alternative model based on the JJ couple scheme for the shell model, where instead of ending up with little m as your quantum number, it ends up with a capital J, the total angular momentum, orbital plus spin quantum number, and projected to the projection M. An alternative scheme using the LS couple scheme, and you couple the orbital angular momenta of individual particles up to the total angular moment, orbital angular momentum L, and then with total spin quantum number into J. So this is the alternative that has been used. So one thing the LSU group was able to proceed deeper and further is to allow the coupling, and not only at the orbital angular momentum, but rather at the oscillator shell that lead into lambda mu, which is the SU3 quantum numbers in the spatial space, rather to call it spatial space, while the spin space remain in its own, and it's coupled to total angular momentum J. Now with the symplectic ERAPs introduced here, one in principle can build even further to have in its machinery the tool to take SP3R ERAPs in the SP3R couple scheme. So what would we have here? So at the lowest SP3R ERAPs, which basically coincide with the SU3 couple, lambda mu, one built the bosonic 2H bar omega states, basis states as its ERAP, all the way up to the total angular momentum. In this way, one can take the collective coherent behavior of particles belonging to different shells into one ERAP. So that's the first part, how David's contribution, and again, together with George Rosenstiel, which I really missed both of them, which has been in its communication, especially with David. And lately, when I was able to get in contact with George's wife, Tetsa, but unfortunately, I was unable to get to speak with George, and until recently, Jerry just mentioned a couple of about an hour ago about his demise. We really, nuclear physics community definitely lost both pioneers of the symplectic model in the nuclear physics. Now, connecting with the quasi-dynamical symmetry, in essence, what we have here, at this moment, we look at the SU3 irreducible representation. In particular, we are interested in pseudo SU3. This is the work by Colin Rumfe when I was at LSU prior my departure to banking world. And we identified that the SU3 quantum numbers labeled by lambda mu's survive throughout different angular momenta labeled by the 0+, 2+, and 4+. Of course, this is very small representation that we encounter, but one can see the survival of the band characterized by the eigenstates of decomposed into an SUT ERAP. While on the other hand, in this quasi-dynamical symmetry of SU3 also exhibit in the context of a single sp3r irrep for erbium-166 given in this slides, where you find the similarity of the eigenstate decomposition is quite striking across different SU3 irreps. One will find that's the result of very high quantum numbers of the SU3 quantum numbers lambda mu in building that the structure. So why this phenomenon occur here? I mean this decomposition are very close, and lately this is the last paper that I was invited by Christina and along with David, and to demonstrate that this particular shape has been exhibited for neon 20 for realistic interaction. And one noticed that throughout, the eigenstates of the spectra, one find the contribution. If one look at the one-dimensional projection, the term of the amplitude and specified in the term of lambda mu's, which basically here labeled as beta gamma, one find a very similar decomposition here. So what I would like to propose here, how one can proceed from here and how we can have a high hope of the success of symplectic framework, not only for light nuclei up to now, neon 20, and then lately even up to calcium, as well as I think close to any upper light shell. This is due to the fact that the interaction, if one can characterize the interaction in the term of SU3 irreducible representation tensor or tensor, it will be only for the limited number, lambda naught, mu naught, and they are very small. Consequently, a similar sp3 irrep tensors will also have inherent the similar structure, while the basis states are with the large lambda mu's. This is similar to what happened with sp3r irreps, unitary irreps for the states. And due to the interaction characteristics represented by the tensors, one can only connect the neighboring lambda mu's in the lambda mu space that bring to the simple diagonalization. So this is what I see, that how the success of quasi-dynamical symmetry, and which exhibits into the very nice good rotational structure, and also can also lead into the the shape coexistence that has been promoted by John Wood, and basically got a stem from David in the last part of his life, will be the direction where this nuclear structure physics will go. So in the end, I could characterize that the quasi-dynamical symmetry works due to the smallness of tensor ERAPs of the interactions. On the other hand, with the large unitary ERAPs of the basis in the framework of symplectic quantum numbers. For realistic interaction that one may face in the future to have a unified picture of a nuclear phenomena across different nuclear species to include the 3-body and 4-body interactions. And the second challenge is really that one has the non-compactness of the sp3r space. However, the reality is we deal with the finite nuclei and with the bound states. So this non-compactness can be subdued by, the competition between the interaction itself that will discard the very high area of the oscillator, excitation states. And definitely, one would love to have sp3r reduced to SU3 Clebsch-Gordon coefficients, which has both aspects, the unitary ERAPs as well as the non-compact ERAPs for the tensor itself. So again, I consider David is strong mentors in bringing this picture together in viewing the complex system in the more unified picture that lead into a promising land that one should be able to come into the conclusion regarding nuclear structure. And the side note that I like to challenge anyone who could bring this thing further, not only in the nuclear physics community of the low energy science, but also for the high energy nuclear physics. And as we deal with the symplectic non-compact space and then the QCD, when we try to give the description of a nucleon or even an atomic nucleus in the term of quarks and gluonic degrees of freedom, one will encounter a non-compact symmetry in this regard. And the study of a symplectic model in the low energy nuclear structure will definitely give some hints how to proceed in the other side of the world, and will bring gluonic and quark degrees of freedom into more satisfactory computational aspects instead of a blind approach using the lattice spaces for the QCD. Thank you very much.